Good morning and good afternoon, everyone. Welcome to Trillium Flow Technologies webinar about troubleshooting vibration in centrifugal pumps. My name is Daniele Davidi, and today I'm here with my colleague Fabrizio Cademartori. We are both part of the centrifugal pump division based in Italy. I'm a dedicated aftermarket service engineer, and Fabrizio to the research and development team. During this session, we will explore common causes of vibration in centrifugal pumps, tools and techniques for data acquisition, and discuss best practices for identifying and resolving them. We hope you find this webinar informative and useful for your daily activities. So thank you for joining us today, and please feel free to ask questions in any time using the dedicated box. Let's start with a few words about Trillium Flow Technologies brand portfolio. Our product brands names are synonymous within the pump and valve industry. With the pump brand, we have Begeman, Flowway, Cabioneta, Rotojet, Wemco, VSP, and Termomeccanica Pompe. For our valves products, we have Atwood and Morrill isolation and checks, Autotorque actuators, Bentley Butterfly, Blackborough control and choke valves, Hopkins PSG, Saracen and Sebim safety valves, Tricentric triple offset butterfly valves, and Randpoint, all leading names in the industry. In the top right pictures, we can visualize Trillium global presence with a supply chain that spans the globe. Our key manufacturing and service centers are located in Canada, China, France, India, Italy, South Korea, UK, and USA. Globally, we have 21 facilities around the world, plus a global network of third-party sales and authorized service center. Utilizing our global presence enable us to tailor the technical and commercial aspect of our product to suit your project needs. Trillium Flow Technologies has a long heritage of innovation spanning 190 years. We're continually adding new products and services to make our customer processes more efficient and productive. In 2020, we added the Randpoint valves to the Trillium family. And these years, we recently are excited to welcome the Termomeccanica Pompe to the Trillium Flow Technologies family. If you are interested to deep dive in our portfolio with a different and complete immersive look, I suggest you to go virtual, visiting our website virtual.trilliumflow.com. So, a few words about our job position within Trillium. My name is Daniele. I have been working for Trillium for 3 years in the centrifugal pump division based in La Spezia in Italy. I'm a service engineer and I handle troubleshooting activities, root cause analysis, as well as design activities for retrofit and overhauls. I work daily with vibration measurement tools, data post-processing, and computational software for structural and model calculation. Please, Fabrizio, if you want to introduce yourself.
Thank you, Daniele. My name is Fabrizio Cademartori. I work in research and development in Trillium Pump Italy, and I am the manager of the Advanced Mechanical Analysis team. And I am a certificated analyst, vibration analyst, and I work both in numerical and experimental analysis using the most advanced technique that are available on the market. And today I'm happy to hear with Daniele to explain our work. Thank you.
Okay. So let's take a look to the agenda for today. We will start with an overview of troubleshooting activities at Trillium, highlighting how vibration issues are current and recurring challenges for us. We will explore the main causes of vibration in centrifugal pumps. After that, a brief discussion of the tool used for on-site measurements. We will see how to identify critical measurements point on pumps. And we will delve into the process of vibration diagnostic, illustrating how to interpret and collect data. And finally, we will have a question and answer session where you can clarify any doubts and delve deeper into the topic covered. So we will start with the first topic about troubleshooting activities overview in Trillium and a focus on our capabilities and standard approach to vibration issue. In this slide, we present a pie chart summarizing the troubleshooting activities conducted in 2024 on centrifugal pumps, divided by defect area. As you can see, vibration troubleshooting issues account for a significant 16% of the total. It's important to note that this functional classification will be made considering only the main cause for which the customer contacts us. But we need to consider that vibration problems may be linked to other area as a secondary cause or contributing factor. For example, an issue with bearing installation can lead to a vibration problem. The same with the opposite scenario, because high vibration during operation can lead to a bearing premature failure. Another good example is connected to excessive bearing oil overheating. In this scenario, vibration would be a consequence to the bad lubricating condition, or as a cause, high vibration can lead to excessive friction inside bearing, and finally increase in oil temperature. Considering all scenario where vibration could be linked, the percentage of troubleshooting activities will increase up to 60%. This is why it is crucial for us to have a structured approach and a well-established in-depth resolution method to meet our clients' need effectively. In this slide, we present another pie chart that showing that all the vibration troubleshooting activities 77% were resolved on site and only 23% remotely. This was both a necessity and but also choice, as vibration issues may occur during the commissioning phase when our supervisors are on site and a deep evaluation must be conducted, or after years of operation due to the natural degradation of the component. In any cases, on-site activities allows for a thorough evaluation of the pump and its operating environment. Being on-site enable us to tailor solutions specifically to the unique condition and requirement of each pump. We can directly monitor the pump's rated condition and performances in its actual operating environment. On-site presence allows us to verify the correct installation and alignment. And finally, we can assess the environmental condition that may affect the pump performances. I would like to add that as a globally present company with various service centers, we are able to assist our clients in the field with specialized equipment and skilled personnel. Okay, so now let's proceed with the second topic. The second topic regarding vibration that most affect centrifugal pumps. In this slide, we aim to clarify that the sources of vibration in a complete centrifugal pump skid, we can have basically two sources of vibration divided by the location where they come from, internally or externally. Internal sources can be mechanical, so originating by rotating components, or hydraulic due to the fluid component interaction. For example, fluid impeller or fluid journal bearing, or also fluid annular seal interaction. External sources are due to the interaction of the skid with the, for example, the plant pipeline or nearby running machinery. But in any case, the combination of these complex sources results in a reaction of the pump and the skid system, which with vibration and noise that can exceed the system resonances frequency and act as a propagation medium for the previous described excitation. So the purpose of this slide is to highlight that the complexity of the vibration issue, where causes and effect can often be combined. At first look, the task seems very complicated, so in order to provide some guidelines, it's important to highlight that, as mentioned in the previous slide, vibration issues can arise during the commissioning phase when the pump is tested in its final installation position, in an environment different from the test room, or after years of use. In this first scenario, it is very likely that unexpected mechanical issues such as misalignment, looseness, or installation problems like poor flatness of civil works or pipeline misalignment will arise. In the second scenario, the predominant factor is the pump wear, leading mainly to the mechanical problems related to rolling bearing failure or hydraulic issues, such as instability of journal bearing for excessive wear and fluid recirculation on wear bearings. So now let's take a look in deeper to the internal sources of vibration. So in this slide, we can see a diagram with three images that represent a skid, a typical skid, one pump, a gearbox that is optional, and a driver. The internal sources that came from a pump can be divided as 1x sources that stand for the vibration that occur at the same frequency as the pump rotational speed. So, for example, imbalance, parallel misalignment, eccentricity. The 2x represent the vibration that occur at twice the rotational speed. So, for example, angular misalignment, ellipticity. The nx refers to the vibration caused by the interaction between the pump blades or vane. So a vibration that occur at multiples of a rotational speed, typically the number of blade or vane. We have also low frequency noise that is represented by a subsynchronous vibration and caused by fluctuation in fluid, and finally other non-synchronous sources that come from other hydraulic problems. So, for example, cavitation, rotating stall, suction discharge, recirculation, vortex shedding, and so on. If we have a gearbox, we have also the NX vibration caused by the number of teeth, so the meshing of gears and pinion. For the driver, we have also, for a synchronous motor, the 1x and 2x frequencies, so that occur at same and twice the electrical supply line. The typical is 50 or 60 hertz. the NX that stand for the vibration that occur at multiples of the pole of the motor. And for synchronous motor, we have the twice of the slip frequency, that is the frequency, the difference between the synchronous speed and the actual speed of the motor. Okay, so let's proceed with a look to the list of our principal tool. Okay, as you can see in this slide, we use dedicated tool for vibration analysis and additional tools for a complete troubleshooting activities, also for the performance of the machine. As a vibration analysis tool, we use data collectors that are tool essential for measuring and then analyzing vibration level in the pump. Providing overall measures, trend, spectral analysis of the signal. The ADRE 408, that is an advanced data acquisition that help us to analyze the shaft displacement, which an interface with a proximity probe. The ODS system, that stands for Operational Deflection Shape. This is a technique to mapping the real movement of the component with use of a lot of sensors. And for last, the motion amplification camera, that is an innovative tool that allows us to visualize and amplify the vibration just with the help of an high resolution camera, so without the use of sensor. And as mentioned before, we use also flow meter, pressure, and temperature transducer to check the correct operation of the pump. Okay, so take a look to the data collectors. Typically, we use data collector with at least 2 channels, allowing us to evaluate both the amplitude and the phase between the 2 signals. These tools enable us to perform overall measurement, trend analysis over time, spectral analysis of the signal, with various sampling frequencies and filters. In addition, it is possible to save time domain signals or synchronize the signals with the shaft angular velocity to create a waterfall diagram. As you can see in the 2 graphs below, in left side we see a time waveform with a very high cyclic impulse. In the right side, we see a waterfall diagram, and we see that a certain time, a certain point in the time, we pass on a resonance because we see a red peak. So in this case, probably the 1x internal source are excited, is the excitation source of the resonance. Okay, now let's take a look to the ADRE 408. This special tool interface itself with a proximity sensor to measure the shaft displacement at a specific point on the pump. Usually, it's suggested to locate there near to the journal bearing, so in the between bearing pumps. Typically, we measure the orbit of the shaft center by combining horizontal and vertical displacement. The signal can be filtered to evaluate the impact of the internal forces on the radial displacement of the shaft. Additionally, this instrument is crucial for assessing the shaft center position during startup, so analyze the proper functioning of the journal bearing, their stability, and also the correct fluid dynamic behavior. This device represents the state of the art for data collector because allow us to an advanced and comprehensive analysis of the failure, but it is very expensive, and the preliminary setup require some advanced capabilities by the operator. The ODS tool is use data to create a visual representation of the real movement of the part. The technique captures how different parts of the structure move and vibrate. The results are typically displayed as an exaggerated visualization, as you can see in the image in the right, that show the amplitude and phase and also the direction of the movement at various points. The acquired displacement can be synchronized with the same mapped point in a virtual space. This tool is very useful for representing the real movement with high accuracy, because it requires a lot of measurement points, but require a lot of time for setup and a lot of data to record. Finally, we present the motion amplification tool. This instrument using an high-resolution camera allow us to visualize and amplify the movement of the entire skid. This tool enables us to visualize the vector, as you can see in the first image in the left. Visualize the vector of the main vibration direction simply by selecting the measurement point in the acquired image. The significant advantage of the motion amplifier is that it allows us to quickly and intuitively identify area of the skid that may resonance, or also to check some installation errors and better understand the main vibration direction and sources. In the imaging below, you can see also a focus on a check installation, and also to check the flexibility and some resonances of the pipeline on the skid. These advanced tools give to the operator a complete overview and visualization of the investigated structure with no necessity to add sensor. In the opposite, the tool provides bad measures if the component has a poor light exposure, or if the vibration that must be investigated is too high in frequency, so the real displacement is quite small. Let's proceed with the measurement point location. We can see the suggested measurement point by ISO 10816. Specifically, we will identify the areas closest to the supports where the bearings of the pump and motor are located. The ISO standards focus, of course, on a potential issues with the bearing, which are the component most subjected to wear. Moreover, these points represent the nearest accessible place over bearing. By focus on this critical measurement point, we can ensure that we are monitoring the most important areas of the pump and allow us to detect any abnormalities. But sometimes the problem could be more complex and not limited only to the internal vibration sources. So, to fully understand the skid behavior under operating condition, natural frequencies of the skid must be investigated. Of course, API standards require verification already at design phase, but often more in-depth analysis are required to support field measurements. So we sometimes, I think almost always, we perform finite element calculation for frequencies and modal shapes and help identify the most relevant areas for measure potential resonances. Of course, we need also to identify the nodes of the resonances shapes, because this point remain, of course, stationary. So if we place an accelerometer in this area, of course, we are not able to capture the resonances. So it is important to strategically place a sensor. Okay, now I want to hand over to my colleague Fabrizio, who will talk about the diagnostic section.
Thank you, Daniele. Okay, let's start our journey in the diagnostic part. Our first step is to outline first and second level strategies. First level strategies consist of baseline measurement of the overall level of vibration and an accurate verification of accordance with standard and experience. Regular measurement must be planned, annotating vibration trends and identifying the presence of pattern between measured quantities that can indicate a problem. In this part, the help of artificial intelligence and machine learning will become more and more important in future. If some potential issues are identified, it is necessary to move to the second level strategies, which involves the adoption of more sophisticated technique and that usually include both numerical analysis and on-site measurement. After the completion of the diagnostic phase, the most effective intervention to mitigate the unwanted vibration phenomena can be defined with the highest probability of success. Next slide, please. Okay. For an analyst, it is fundamental to understand the interaction between hydraulic and mechanical phenomena. We can mainly differentiate three different types of vibration. Free vibration that occurs when a single event excites the system that then vibrates at its natural frequency with an amplitude that is proportional to damping. The forced vibrations that are generated by a periodic excitation force, then the system vibrates at the forcing frequency, and the amplitude is function of damping and separation margin between excitation and natural frequency of the system. Self-excited vibration occurs when there is a feedback from the vibration instructor and the excitation mechanism. A typical example is the force generated in sleeve bearing and annular seal. If damping is sufficiently low, a self-excited vibration is created. While free vibration are really significant in pump operation, forced and self-excited vibration frequently causes problems, which can be classified as lateral vibration measured by proximity probes, or torsional vibration due to unsteady torque from the motor, and so on. It's very important to fix an issue related to vertical pump, since in this type of pump, journal bearings have no defined loading, so they are prone to instabilities. Next slide, please. Okay. To make our journey without losing our way, it is necessary to have a map. Our map is created by experience in pump field. It is useful for the interpretation of vibrating behavior to use these elements. The number of stars that you see in the picture near to each causes is proportional to the likelihood of the problem occurring. We must understand that each vibrating source has its peculiar signature, which the vibration analyst must be able to recognize. In rotating machine, the most common symptoms is synchronous vibration. The spectrum is characterized by a peak at the rotating speed, and the orbit shape is almost circular or elliptical. the key phasor signal, a red dot, usually remains almost in the same angular position. There is weak or absent flow dependence, especially if you are talking about mechanical unbalance. The common causes are mechanical unbalance located in coupling or foreign matter cooked in the impeller, hydraulic unbalance due to uneven flow in the impeller, operation at critical speed, and in this case it is required a review of our rotor dynamic calculation, or very low damping in journal bearing, or excessive runout, bobo shaft, and so on. If the rotating speed has a limited separation margin with natural frequency that involves bearing bracket or foundation, a dynamic amplification can happen. And also piping alignment errors or casing distortion can cause a synchronous vibration. Next slide, please. Our second step is subsynchronous vibration. In the spectra, we see peak below running speed, and there is a tendency to a chaotic orbit where the key phasor marker move constantly. If amplitudes jump to excessive level above threshold frequency and the flow dependence is weak, rotary stability generated in bearing or seal is a possible cause. Bearing problem can be both the root cause or the symptom, with bearing damage caused by excessive vibration introduced, for example, by resonance. Rubbing in annular seal can also create a chaotic orbit. Anywhere, the chain of the event to cause and effect is not always easy to understand. For example, high amplitude lead to wear of the annular seal, increase the seal clearance, reduce the rotor damping, and then vibration increase, and so on, causing increasing wear in the seal. Finally, if the peak in the spectrum is proportional to speed with amplitude increasing with speed, a rotating stall or a circulation is possible. Next slide, please. If we talk about subsynchronous vibration, it is necessary to focus on whirl and whip. Whirl is a self-excited vibration caused by fluid dynamics with the bearing, typically occurring at a frequency slightly less than half the rotating speed. It is more or less stable and does not increase in amplitude indefinitely. When the whirl frequency coincides with the natural frequency of the rotor system, leading to a resonance condition, whip occurs. The vibration amplitude can increase significantly, causing instability and potential damage, and its amplitude is limited only by nonlinear effects such as rubbing. The orbit plot for whirl is circular or elliptical, with two key phasor dots moving since the phenomenon is not exactly synchronized at half the running speed. In contrast, the whip orbit is more chaotic and we have multiple dots. The most useful diagram to observe this phenomena is the waterfall full spectrum, where it is possible to see the transition between whirl and whip when the vibration frequency remains constant while changing the rotating speed. Next slide, please. Okay, our journey now arrives to blade pass frequency. If the spectrum shows peaks at rotating speed and harmonics of blade pass frequency, that is the rotating shaft frequency multiplied by the number of impeller blades, and the orbit looks like a flower, a daisy, for example, with as many petals as there are blades in the impeller, then a periodic force generated by hydraulic interaction between rotor and stator is active. With an unfavorable combination of impeller and diffuser vane count or acoustic resonance with blade pass or mechanical resonance of bearing support, we can see orbit and spectrum similar to those in the picture. And regarding supersynchronous vibration, there is a very interesting paper related to a pump with inducer, but this part is out of scope of this webinar. Next slide, please. Okay, now we arrive in a very interesting place, misalignment. If we have dominant vibration at twice the rotating speed plus a synchronous peak and other harmonics, misalignment that can be parallel, angular, or probably both is the cause. The orbit changes from circular to banana shape. In case of severe misalignment, we can see a shape similar to an 8. There is a weak dependence on flow in this case. Loose part instead create peak in the spectrum that can extend above 10 times the rotating speed. And rotor rub has a similar characteristic to rotating looseness, but half order harmonics are present in the spectrum. It is not rare that one or more resonance can be excited by rubbing. If we see broadband vibration at low frequencies that increase towards zero with irregular orbit, then we have recirculation in our impeller. This phenomenon is more accentuated when we have low flow rate. Next slide, please. Okay. This is a very important part of the presentation. Since in this slide, I want to underline that if we do superficial analysis, we can cause severe errors in our diagnosis. The key to understand the vibration is always to achieve a comprehensive view of the symptom, a big picture. Rotor rub and fluid-induced instability are compared in this slide. As you can see, both orbits contain a mixture of synchronous and subsynchronous vibration. They are called frequently rabbit here, as you can see in the orbit picture. While fluid-induced instability is predominantly forward at the subsynchronous frequency, the rub orbit contains a significant reverse precession components. Moreover, for fluid-induced orbits, the key phasor dot moves, since the phenomenon is not exactly at half the running speed, while for rubbing, the orbit is looked at this subsynchronous speed. You can understand that if we limit our analysis only to half spectrum, it is quite easy to make confusion between these two phenomena. While if we use a full spectrum and we analyze deeply the orbit, the difference is more clear. Next slide, please. Okay. Now we arrive at resonance condition. The most evident symptom of resonance is the presence of peaks in the spectrum that are not related to rotational speed. If it is possible to vary the rotor speed, the position of the peaks on the spectrum will not change. It is important to understand that resonance is not only excited by a close by discrete excitation frequency, but also by broadband mechanism such as partial load, recirculation, turbulence, and so on. And regarding cavitation, normally it creates a random high frequency vibration or noise. And our last phenomena in the map are peaked grid frequency related to electrical perturbation, peak at motor speed that could be transmitted via base plate or to the pump, and anti-friction bearing issue that I will explain better in the next slide. Next slide, please. Okay. Anti-friction bearing have different damage stages, and to understand it, we must use different technique. The earliest indication of bearing problem appear in ultrasonic frequencies. To detect that, first symptoms, ultrasound or high frequency vibration technology are required, for example, envelope. At stage 2, the bearing deterioration progress and the intensity of the impact forces has increased sufficiently to excite, like a bell, the natural frequency of bearing components. At stage 3, reading continue to increase. In addition, specific bearing defect frequency appear in the spectrum. I put some formulas in this slide to calculate this frequency, but you can find it in all the catalog of manufacturer. Stage 4 is final stage of bearing deterioration before total failure. The discrete bearing defect frequency disappear and are replaced by random vibration in the form of noise floor. As shown in the picture on the left side of the slide, you can see that 50% of damage in anti-friction bearing are caused by lubrication problem, poor lubrication or contamination. So take care about it. Next slide, please. Okay. This is a very peculiar part of my discussion, since it's not uncommon that for monitoring large pump, we have to measure both vibration in terms of velocity and of the bearing housing and shaft displacement with proximity probes. Sometimes it is observed that shaft vibration are quite low, whereas bearing housing vibration exceed the allowable limits considerably. In other cases, shaft vibration exceed the allowable limits, while bearing housing vibration are quite low. For the first condition, rotor dynamic is probably okay, but for example, the resonance of bearing is possible, while for the second case, shaft rotor dynamic is problematic. A non-uniform pressure distribution in the stator causes a static bending line of the shaft, with alternating stresses and risk of shaft breakage due to fatigue. In the absolute system, the orbit is reduced to a radial displacement, while in a relative reference frame, the orbit is almost circular. In contrast, with a non-uniform pressure distribution in the rotor, the shaft rotates in its deformed state, with a static bending stress in the shaft. In the absolute system, the orbit is pretty circular, and in the relative reference frame, the orbit is reduced to a radial displacement. Okay, next slide, please. In this picture, I want to show you an example of an activities that involves both aftermarket department and research and development department. We have a boiler feed pump with a vibration problem, and what we have to do now? We have to go back to our map and try to understand the symptoms that we have for this pump. In this case, we have high vibration at synchronous speed, peak in the spectrum that follow the speed, weak flow dependence, And another important point is that vibration change when we change the rotating speed. Okay, if I go back to my map, I will see that probably we are facing off an imbalance combined with a resonance condition. So the second step that I must follow is to make some confirm to my hypothesis. First step is to perform an hammer test, and you can see in the central part of the slide that when I make my measurement, I see that I have a natural frequency near to the rotating speed. After modification to the base plate, I see that this natural frequency is shifted over the rotating speed. And these modifications are determined with the help of a detailed FEM analysis. Okay, after the implementation of all of this modification, I can see that the vibration in my pump is highly reduced, and we reach a allowable vibration level, and we have success in our work. Next slide, please. Okay, we have reached the end of our journey, and now we see how deep is the rabbit hole. However, I want to leave you with some recommendation. First of all, it is necessary to plan a campaign for the acquisition of vibration data. It's important to store and classify this data. They will be very useful in future. And it's also important to search for trend and relationship between functional parameters. And I'm sure that in future, machine learning and artificial intelligence will be more and more important in this field. A second point is that interaction are the keys. Both external interaction due to pump connected to the system, piping, motor, gearbox, baseplate, and so on, but also internal interaction between rotor and stator, and between shaft and bearing. Another point very important is that you have to follow the signal. You must have a big picture of the problem, and do not limit your analysis to just creating a fast Fourier transform with an accelerometer. And last but not least, vibration analysis is a combination of technique and experience. So always ask to experts. Thank you. That's all for my part of the presentation. And next slide, please. We are here to answer all your questions if you have some of it.
Okay, let's take a look to the Q&A box.
Okay.
Peak follow speed. Please elaborate on this.
Okay, and we are talking about unbalance, and unbalance is a force synchronized with rotating speed. And so if we change the rotating speed, the frequency of the in the spectrum change as the rotating speed with the rotating speed. In these terms, the peaks follow the speed. If we are facing off resonance, peaks are not related to the forcing frequency, but are related to the mass and stiffness distribution in the system. So peaks remain in the same position also if we move the rotating speed of the shaft. You're welcome.
Yeah.
Another question? Condition climatica con temperatura negativa. Okay.
Yeah.
If you want to answer.
Yeah, I suppose that with high variation in temperature, maybe the structural behavior of the entire skid may change. I think that the resonances of the system may have a variation in frequencies that may change if the external temperature changes. But I think there is no high dependence from the internal excitation, mechanical or hydraulical excitation of the pump, depending by the temperature. I think. I don't know, Fabrizio, if you want to add something.
Yeah, I want to add something. For example, it is important when we have journal bearing to control the oil temperature, since the performance of the oil is strictly related to the temperature. And usually we have devices that are able to control the temperature of the oil and limit the maximum value. And so we can guarantee that the pump will not have any damage due to unwanted higher temperature of the oil. And regarding other parts, also very cold temperature can become critical if you are talking about, for example, rubber pad or something that has damping properties. But we must take care about it during design phase, so we can face off every condition, and we are sure that we will not have a vibration problem during operating condition.
Yeah, there is a question from Gomez. Once the vibration starts at the bearings, how fast it increases? I think that it's depend by the stages we are in the failure. If we are in the early phase, the increasing in the failure is, I think, quite slow. It's difficult to see how slow, but I think weeks or months. If we are looking to the 6-4, the stage 4 of the bearing phase, this stage is very quick and detrimental to the reliability of the bearing.
Yeah, I agree, Daniele. If we are in stage 4, probably we are late.
Yeah,
and,
too much.
As you remember in the presentation, the most important point for bearing is lubrication. So if you have good lubrication, I think that also in stage 2 or 3, we can say that we have enough time to planify an intervent to resolve the problem. If your oil is not good or you have contamination, you have very few time. So first thing is take care about lubrication regarding anti-friction bearing. Apply hydrodynamic lubricated oil bearing in your pump, which give better damping. Yes, it's true. If we have anti-friction bearing, the only damping for a pump is related, for example, to annular seal and to the interaction between stator and rotor. If we have a journal bearing, also the journal bearing has an internal damping. But there is another difference. Journal bearing can have whirl and whip problem, while anti-friction bearing does not have this problem. So it's important to choose the right bearing for our application.
Yeah. I think we can close the meeting with the last question because it is very interesting from David. In your experience, when vane pass is dominant vibration on the pump, what is the main cause? NPSH RVS versus NPSH available, wrong hydraulic analysis. So, which is the design or operational condition that can increase
Okay.
the blade or vane pass?
I,
Yes,
do
please,
you
Fabio.
want to? Okay. My first answer is a joke. Our fluid dynamic analysts are very good, so they design a very
Yeah.
good impeller without blade pass problem. But it is a joke. Sometimes we have to face off this problem, and I must admit that the most common problem is not related to hydraulic, but is related to resonance with a bearing support. In this case, it is very common that you design your pump and you can face off a problem of high vibration, and you can resolve changing the bearing housing support design. But also NPSH can be a problem. But probably if you have a problem of NPSH, you will face off a sort of different damage, for example, cavitation and so on. Daniele, do you want to add something?
No, I think that the answer is correct.
Okay. I think that we
Okay.
didn't answer to all the question, but you have our email in the picture in the next slide, probably, Daniele. And we
I
are
don't remember. Yes, but it is the mail from for Trillium, and you can text all your question, and we try to make our best to reply to you.
yeah. We will be happy to answer to you because this is our work and we enjoy doing it.
Yes.
Okay.
Okay. Thank you for the attendance, and really appreciate. Bye
Thank you
bye.
very much.